Ladies and gentlemen, welcome to the IET London Savoy Place. There are no scheduled fire alarms for this evening. If you hear the alarm, please go through your nearest fire exit and make your way to the meeting point under Waterloo Bridge. Staff will be on hand to lead the way. The President's address will begin shortly, so please take your seats and ensure your mobiles are turned to silent. Thank you. Ladies and gentlemen, introducing your speaker and IET President, Mike Carr.
When you watch TV, I doubt you realise the level of innovative engineering that is being used in the journey of these television images. When I helped build the first digital video conferencing systems nearly 50 years ago, we never imagined that those very techniques today would enable us to view hundreds of high-definition channels live or watch millions of videos straight from your smartphone. In my talk about digital television and data compression, I'll explain what was invented, how it was developed, as well as give a look to the future of digital TV.
Please welcome to the stage, Mike Carr.
Thank you, everybody. Thank you very much for coming. It's great to be here. Yet another packed audience here at Savoy Place. Also, thank you very much for the people that are listening online on IETV. So we've got a lot of people to present here today. It's a great honour for me to become the 148th President of the IET. This evening I hope to demonstrate to you some of my personal enthusiasm for technology and engineering through talking about picture coding. I'd like to start with an introduction to my early career. As a youngster, I was always interested in science and technology. By the time I got to secondary school, I was already interested in electronics, waiting for practical electronics to come out each month so I could go and build something, waiting for the next innovation that I could actually go and try. And I was so interested in the practical side of electronics that when I got to 16 years old, I decided to leave school with only a few qualifications and become a technician apprentice with BT. It was called Post Office Telecommunications in those days, but I did a 4-year apprenticeship so I could get my hands on the electronics rather than just study about it. So I spent 4 years as an apprentice up telegraph poles, down holes, fixing telephones, fixing telephone exchanges eventually. And I really did love it. I thought it was just exactly what I did want to do, but I thought I'd better go and get a degree. Fortunately, as part of the apprenticeship, they'd sent me off to college, to Mander College in Bedford, in order to study for a telecommunications certificate from the City and Guilds. And that allowed me, in order to apply to go and do a degree, which I started down in Plymouth, a 4-year sandwich degree in communication engineering, which was also really interesting for me. Now, it was while I was down in Plymouth that Dr. John Thompson, who's somewhere in the audience, somewhere over there, came to Plymouth and did a really great talk on the work that he had been doing on digital television. He already at that stage had spent 10 years working in the area as one of the very early engineers researching this subject. And his talk caused me to apply in order to go and join John's division of BT Labs at Martlesham. John had by then set up a fairly substantial research division in visual services. And I was lucky enough to get a job there, and I came and worked for Dr. Richard Nicol, who's also somewhere in the audience here. And I stayed there for 14 years. 14 years working on the practical design of video compression systems, doing the basic research, eventually doing the development, and then finally going to the international standards organizations to get the thing standardized across the world. So I had a really fantastic time, and it's really the motivation for my talk this evening. If you think about it, this technology is just everywhere. There's billions and billions of occurrences of it. It's in set-top boxes, it's in DVD players, it's in television sets, it's in every smartphone, it's in most digital cameras these days. So there's literally billions of occurrences of this video compression technology. And yet, as far as I know, I haven't seen a presentation that really talks about it in the sense of a new engineering technology. So I thought that would be a good subject for me today. The reason I like it, and I was sort of personally interested in it, is because you're always challenged in terms of the hardware that you can build in order to do the processing. You're always challenged in the amount of processing that you can do. And it also takes advantages of the human visual system. There's deficiencies in the human visual system that you can take advantage of in the compression, and I'll talk about that during the talk. So let's get started. We've had 50 years of mechanical TV, starting in the 1880s through to the 1930s. This culminated in John Logie Baird coming up with a transmission system to connect an encoder and a decoder. It simply worked by shining a light through a rotating disc that had a spiral set of dots in it, which scanned the object that you were wanting to look at with a light, picking that up with a photosensitive cell, relaying the output of the photosensitive cell to the far end, and then recreating the image by looking at another rotating disc at the far end. But it worked. It was very crude, but it was the basis for television going forward. We then had another 50 years of analog TV. Really, from 1930 was the very first commercial transmissions, and it grew and it grew and it grew, and we all know that. But sort of by the 1980s, it was almost a human right to have a television set in your home. And then came the 1970s, where we could just about store a digital picture, a single frame of video, in digital memory. The problem was that memory, firstly, wasn't fast enough up until that point in order to take a television picture and digitize it, and there wasn't enough memory, and it took some 30 or 40 circuit cards to build one memory in order to grab a single frame and store it. But once you've done that, you could really think about image processing using computer techniques in order to manipulate the image in ways that you couldn't possibly do in the analog world. So we started working on digital TV. Some people, John started working on it in the late 1960s. It really got underway in the 70s, which is luckily when I joined the research lab at Martlesham working for Richard Nicol. The problem we had was not only was it hard to build a frame store, analog to digital converters, the thing that took the analog TV signal and sampled it and turned it into digits, cost tens of thousands of pounds. Color cameras were tens of thousands of pounds that had only really just been invented at that stage. And more importantly to a researcher, you couldn't really record video in any successful way. Videotape was just about coming out. You could make a record of what you were working on, but if you wanted the same test sequence over and over again in order to be able to work out whether the video coding scheme you were working on was better than yesterday's, unfortunately the tape would wear out. After about 15 plays or so, they were pretty well unplayable, so you couldn't record images in that way. And I'll talk about that a bit later in the talk. So what is the problem that we're talking about here? Digital television that we have today, a typical television picture that you're looking at in your home, has a couple of thousand pixels, dots in a long row per line, and literally 1,000 lines on a typical image. If you allocate 8 bits to the red signal and 8 bits to the green signal and so on, and add them up, then you end up with a bit rate requirement of 1.2 gigabits per second coming from the image. 25 pictures per second is a pretty low frame rate. A lot of televisions these days operate at much higher than that. In those cases, you would end up with a much higher bit rate. Unfortunately, bandwidth that's available typically for these purposes, either over a satellite or the digits come into your home, is only around 2 megabits per second. And so you would need a compression ratio in order to fit this over a 2 megabit per second channel of something like 600 to 1, which is a very tall order for data compression. A lot of you will be using things on your computer which claim to compress your data. These are data compression schemes that basically just look at the data itself. Typically, zip, as it's known, or WinZip, will achieve something like 20 or 30% on a web page. The reason that it can compress a web page by 20 or 30% is because there's a lot of redundancy in a web page. HTTP // could be replaced just by one character, for instance, meaning HTTP // But the things like images and sound and other things that are in the picture are not compressible. And so ordinary data compression algorithms might give you 10, 20, if you're lucky, 30%, occasionally 50%, but nothing like the 600 to 1 that we need in order to achieve video compression over a 2 megabit channel. So the only way that you can do that is to look at the picture rather than the data. We used to have people turning up at BT Labs, probably about one a year over the period I was there, that would claim that they'd come up with a data compression algorithm that could compress any data by a factor of 2. It simply can't be true. You can prove it by giving them some data to compress and then asking them to compress a second file, which is the data file that they gave you. Clearly, it depends. It obviously depends on the amount of redundancy in the image. So the only way to get away from that is, as I say, in order to look at the inside the picture rather than the data itself. Now, when we started this work, there was no business case at all for broadcast TV. It's interesting, it's heavily used in broadcast TV these days, but looking back to the 70s, there was a perfectly good transmission system. It was one transmitter serving about 500,000 homes. So the cost of that was divided by 500,000. Everybody had a receiver, an aerial on their roof that could receive that signal. It was only one-way transmission, and there were only 4 channels. So there was a massive amount of bandwidth available between transmitters and receivers for 4 or 5 channels, and there was no business case, therefore, in order to think about digital compression. So we focused on person-to-person video. In this case, you essentially need 2 transmitters and two receivers, one of each kind at each end, and you need a personal transmission link between the points. And obviously, if you're going to take a whole radio bandwidth worth of bandwidth in order to do it, it's not economic, and you can't do person-to-person communication. So we focused on video communication for people. That's an early prototype. You can see that there's not even any buttons on the keyboard in front of the gentleman. And video conferencing, where you essentially sat in a studio and you looked at the picture of somebody the other side of the world, and you could clearly talk to them. Now, video conferencing for picture compression has a number of great advantages. The camera's still. The background doesn't move very much. actually the people don't move very much, and the lighting is extremely good. So as a starting point for compression, it's a much easier set of circumstances. The more difficult part is that it is real time. You're trying to connect one person to another in an interactive discussion, and if you spend too much time on the video compression, then you can end up losing the interaction, and therefore you've got this challenge of delay, which limits the amount of processing that you can have. Now, if you're in a research lab and you spent any time there, you'll realise that the people that pay the money want to know that the research that you're doing is really good. And so you're constantly asked what the future looks like. I managed to come across a piece of film, actually, because video wasn't around in those days, that came from the Post Office Research Labs at Dollis Hill, which was trying to look in the 60s, in the mid-60s, what television communication or person-to-person communication would look like in the 90s, so 30 years on. So it's quite brave to do this. It's equivalent of us asking ourselves today and making a video about 2050. So here's the video.
Through to Mr. Harbottle. Do you want vision?
Yes, please.
Press the vision button.
Good morning, Miss Johnson.
So they got
Nice
this
of you
bit
to ring
right.
me.
Small
Now,
television
about
camera,
the
colour
original
picture,
release.
small unit.
I understand you had second thoughts about it.
Yes, it's the proposed new road that's worrying me.
I've got the plans here. It may help if you see exactly what the proposals are.
No, they got this bit right as well, I think, a high-resolution transmission system.
Documents like this are transmitted in accurate detail by a slow-scan high-definition process.
I'd like to take a copy of that.
Yes, I think you should.
I don't think they got this bit right.
Pressing this button suffuses the screen with ultraviolet light and imprints the copy on the photosensitive paper.
Now, how the image comes this way round, I don't know. So I thought it was quite amusing. So, but I bet we would be caught out in exactly the same way if we tried to make a video about 2050. So how did these early image compression, data compression systems work? Well, we started with 2 megabits per second. 2 megabits per second was a bit rate that was being developed for technology which interconnected telephone exchanges. Basically, subscriber trunk dialing, STD, was really catching on in the 70s, and interconnecting telephone exchanges with telephone wires was getting quite expensive with copper. And so using the existing copper wires to interconnect the telephone exchanges where you could put 30 telephone calls across a single copper wire was in development. So we chose 2 megabits per second as the bit rate that we would try and get a television picture down. We couldn't, though, get international links, and we started off with an international collaboration in Europe. It was just impossible in order to get a fixed line transmission system which would even connect between the UK and France. So we were very fortunate that at the same sort of time frame, the orbital test satellite was launched by the European Space Agency in 1978, and we managed to get many hundreds of hours, several hundreds of hours actually, on this satellite. We had to build an Earth station first. You couldn't even buy an Earth station, so the labs had to build an Earth station and use the test satellite in order to interconnect Germany, France, Italy, and the UK. And with us each doing experiments and then interconnecting the results on a regular basis, we could optimize the video coding schemes that we were working on that way. Now, because of the investment in satellites, and it was very interesting, and the investment that was going on in digital communications and video compression, there was a range held in this very room, in this precise spot. And my very first science papers that I ever wrote or published were actually here in this room. They're in the archives of the IEE, or the IET now as it's known. But this really did form a community around digital transmission, digital satellites, and the work that we were doing on image coding. So what was the problem with the first image compression schemes that we were developing? We challenged ourselves with quite a lot less pixels. Instead of a couple of thousand pixels per line, we had 308. 256 of those were black and white pixels actually, and we added 52 on the end to give the picture some colour. 144 lines rather than the nearly 1,000 lines that you get in today in your HD type pictures. If you do the maths on it, 8 bits per pixel, 50 fills per second, you end up with about a compression ratio required of about 10 to 1. 18 megabits is what the picture results in. You could get about 1.8 megabits you've used one channel for audio and so on. So 10 to 1 was the challenge, and at the time that seemed a heck of a lot. You certainly couldn't think about doing anything like that in the analog world, and the challenge was, could we do it in the digital world? Now, as I explained to you, the videotape recording mechanisms hadn't really matured at that stage. They were just being tried, and we couldn't repeatedly get a source of video to work on, and we needed to do that. So we developed this. Meet Dolores. I can assure you this is not some attempt to correct the gender imbalance in our laboratory. But it was a stable source of video. Cameras were very stable, and you could play this each day and check that the work that you were doing on the next day's video coding was better than the previous days in some way by watching this. We did improve Dolores. And without any exaggeration at all, in an effort to optimize the various coding algorithms that we've tried, I have spent several thousands of hours watching this picture. As far as I know, it's had no effect whatsoever. When I was thinking about that last night, I didn't think I was going to get away with that, but I did. I was pretty pleased with that. So the first thing you do in these video coding schemes is think about only the things in the picture that's changed. It's clear that you've now got a frame store, a store that can store one picture's worth of data. So you can put that at the decoder, and you can just send the changes. So the first thing you do is you look at the parts of the picture that have changed and just transmit to. The second thing you do is try and take advantage of the deficiencies in the human visual system. And this is quite a tall ask for this experiment, which I'm going to do, because it depends on a few things: where you're sitting, what the brightness is of the screen, and whether you remember to bring your glasses or not, but we'll have a go. So I'm going to describe the area in blue there as a low frequency area. If you think about the waveform that might describe it, it's a straight line. It's a straight line of blue. There's no changes across the width of the circle. I'm going to think of another area here, which is the higher frequency area in the picture. If you think about the waveform that might describe going across that, it's going up and down with the crevices, the bright snow, the dark crevices, the bright snow. And so I'm going to call that a high frequency area. And what I'm going to do is I'm going to look at the scene now, and I'm going to add some noise, and then I'm going to do a test. Can people see the noise? If I just flip backwards and forwards, who can see the noise? Can the people at the back see the noise? Well, I'll put more noise in, but the point is, if you look at it, and you might not notice until I tell you, but you can't see the noise being added to the mountain. You can only see the noise in the sky. And it's because the noise is being added linearly across the picture. It's because the human visual system is such that you can obviously detect the high frequency noise in a low frequency area, but you can't see the high frequency noise in a high frequency area. And that's an advantage that we try and take advantage of. I've added quite a lot more noise now, 75% noise. I don't know what 75% means, but you know, it's like any other political statement. It's 75% of something. There's the plane area. And again, I can see just about something happening on the mountain. I can see clearly on the low frequency areas of the lake. And if I go to 100% noise, which is, you know, let's do that, 100% noise, then it's still difficult to see without an A/B comparison. So what do? Well, we use something called predictive coding. So this is a very low resolution picture now. So each mauve dot represents 1 pixel. Of course, the whole thing would be scaled much more than this in detail. But think of all the purple dots as being ones that you've already sent and the decoder's already decoded. So you send these in sequence from the top left. You do your first row, and then you do the second row with B, C, D, and then carry on, and then you do the third row, and you've just transmitted pixel A, and you want to send to the decoder pixel X. So the X is the one that we're all talking about. Both the encoder and the decoder have got A and D and all of the surrounding pixels because they've already decoded them. What we do is we make a prediction in terms of what the value of x might be by saying it's A plus D over 2. So it's an average of the pixels that the decoder's already got. It can make a guess. The encoder can make a guess. And you send the difference between the guess and the truth. So that's predictive coding on pixels that we use. And if you think about it, and again, this is ridiculously low resolution, but it demonstrates the point. In the low frequency areas, in the sky, A plus D over 2 is going to be perfect. The guess that the encoder and the decoder can make is perfect because the guess for x will be A plus D over 2, which will still be that plain blue colour. If we go, I meant to do that clip before, but anyway, we'll move on. If we go to the more detailed area of the higher frequency area of the mountain and try and do a prediction, we could be massively out because A might be sitting on snow, D might be sitting on snow, and X might be in a crevice. So the guess that the encoder makes and the decoder makes will be radically wrong. So combining those two things, we put them into this table, and I apologise for the table, but it's the only way I could think of explaining it. Basically, where the differences between the prediction that the encoder makes and the decoder makes is small, we send it very accurately. Where the prediction is very large, has a very large area, so say the prediction was 100, we send it very crudely. There's massive difference, the whole range from 125 to 255 in the badly predicted areas, but very accurate transmission of the difference between the prediction and the actual value in the low frequency areas. And similarly, we send short codes for the highly predictable areas and long codes for the more difficult, unpredictable areas. And this is a variable length code that always ends in 1, so you can string them together in any order, and you can see that you might get 0, 1, 1, 1, 1, 0. You can effectively decode it. But the point is that you're only using the very long codes very infrequently where the prediction is wrong, and you're using the short codes most of the time where the prediction is good. And the net effect of that is to both give you a lower bit rate, because most of the time you're using just the 2 bits or the 3-bit codes rather than 8 bits per pixel. And for the high frequency areas, then you use the long codes, but they don't happen very often. So we built one of these in 1982, this picture, 44 circuit cards, would you believe, just to do this, in a rack of equipment, black and white camera, and we added 52 pixels at the end of the line to make 308 pixels, giving us colour. And this is the actual result. I think this video is dated 1983 because colour was added. So the first person you see is Richard Nicol, looking a bit younger. Second person you see is me, looking about the same. Actually, a lot of the loss in performance there is to do with the video recording. I really do think it did look better than that. That's the 20 of the 44 circuit cards were actually in the thing. And we were lucky enough to work with GEC Marconi at the time. Basically, we were doing the research. We came to an arrangement with GEC Marconi to do the development for us and produce the product. And we produced 80 of these things and sold them throughout the world at £40,000 each. So it was a really good business for one lab to be involved in. But for me as a researcher, this was absolutely fantastic because you start on a research project, you don't expect to see a product. And yet within 4 years, we had a product in the international market selling better than anybody else. We had something like a 90% market share with those 80 video conferencing systems at the time. And it was a really good achievement. So it was clearly I was very proud of that. The team were very proud of that. And we also managed to get it on Tomorrow's World. Tomorrow's World was, the premier science program for 10 million viewers every Thursday night at 7 o'clock. So for a young chap to see the work of the team on Tomorrow's World was really great. This is the Tomorrow's World program.
Hello, Nora.
Hello, darling.
I shall be home in 10 minutes. Is dinner nearly ready?
Not nearly, but in 10 minutes it will be.
Got something good?
Telephones that let you see the person you're talking to have been predicted for years. But the technical problems of sending television pictures down telephone lines have proved much more difficult than science fiction writers imagined. So how much longer must we wait to see real-life scenes like this?
In 10 minutes. Bye-bye.
Bye-bye.
So British Telecom have designed a device that takes advantage of the animator's trick, first is and then only sending the moving bits of the picture down the telephone line. It does this by storing each picture that comes in from a television camera for a fraction of a second and comparing it with the previous one and only transmitting the difference. On the other end, each picture is remembered and continuously updated by the transmissions coming in. The device is operating at British Telecom's research facilities now, and we've set up a line that connects it to this camera, and they're sending the processed pictures down the line back to us, and hopefully it should come up on this monitor any second now. Ah, there it is. Well, I think you'll agree that that's a remarkably good picture. But most of the picture that you're seeing is actually in the memory store of the device. Switch off that memory, and you'll see only the parts of the picture that are being transmitted, the parts that are moving. So if I keep still, you should just see my lips and my eyes, if I move them. And if I move my hand in to scratch my face, you should see that too. Turn the memory back on, and the whole picture is back. The only way that you'll detect the economies in the novel method of transmission comes if I make huge movements like this. And as you can see, it's rather difficult for the picture to catch up with me.
Now, the thing is, we were very pleased with that, but having worked for many years for BT, you do get used to being criticised by the public, and even the BBC couldn't resist the temptation for a polite dig. Just watch this.
But even these pictures need 30 telephone lines, so it looks as though it will only be of interest to big corporations at the moment. But if you want to increase your phone bill by 30 times, then I'm sure British Telecom is waiting for a call from you.
We definitely tried. Well, as a result of doing this, the world really did rally round and realise that these Europeans had got together, France, Germany, Italy, ourselves, and built this codec, and they better come up with a world standard that worked at lower bit rate and higher resolution. So the next 5 years, my career was involved in the team with Richard, going to international standards bodies, working in the lab on research, and defining the next generation of standard. As I say, it was targeted at far more resolution than the 300 pixels that we had there, and it's now known as H.261, and many of you may well have heard of H.261 because it's in use in everything today. So, in order to describe what actually went into this codec standard, there was lots of different things tried, but I'm just initially going to talk about the things that went into the standard, and then that didn't. So here I've got an image. It's from a famous test sequence. We all used to share test sequences so that we could all work on the same images. This is called Foreman. It's actually something like a minute long, but I've just taken 2 frames from it. Frame 2, frame 1. So frame 1's that one, frame 2 is the next one. So they just orientate yourselves to it. It's just 2 images in this moving sequence. There's a number of things happening. His hat's going to the right, depending on the order that I show it, of course, but if you know that's frame 1. The building's going slightly up. The actual camera's coming down, I hope, rather than the building moving, but you know what I mean. And his tongue's coming out, so just to get those 2. And if I take the the differences between those two images, then I end up with this. So because we can now store multiple frames, memory's a lot cheaper now, memory's a lot faster, it's 10 years after when the first set of work was started, you can think about storing multiple images, and so frame differences become quite useful. Now, if I look at the two images side by side, frame 2 on the right, frame 1 on the left, they look like the same image fractionally moved. Of course they are. So I can create something called motion compensation, where what I do is I look in the frame that I'm about to send and see if I can find those same group of 8 by 8 pixels in the previous frame, because the decoder's already got those. It's already been sent. It went a 50th of a second ago. And so I have a search algorithm that looks at his lips and sees if it can find it in the previous frame. Now, those lips are not in the same place because they have moved between the frames, but they are the same lips. And if we look at the motion vectors, as they're called, the little black lines represent where everything in the image has gone between the two frames. You can see his hat's moving to the right here. You can see his lips just coming up sort of on their different direction to everything else, and the building's moving very fractionally, so very, very small dots. And by transmitting these vectors for 64 pixels each, 8 by 8 pixels, to the far end, I can just move the previous image around to create a new image. And that saves me sending pretty much any new pixels at all. It's just a movement of the previous picture. So on the left there's the original difference image, which I took as the difference between frame 1 and frame 2. And on the right is exactly the same thing, but the difference there is between the motion compensated version of the image and the actual image. And you can see it's pretty close. There's very little information to actually residually transmit in the right-hand image. So the first thing that was added to H.261 was this thing called motion compensation. The second thing is a bit harder to describe, but it tries to take advantage of the same thing that I talked about before, where your eyes are not very good at seeing errors in the detailed areas of a picture. So if we take the boardwalk there and look inside the 8 by 8 flashing square, just here, this I'm going to try and describe to you as having very low horizontal frequency. If you think about the waveform that might describe that plank, it goes across the plank and it's a straight line. If you think about going across the 8 by 8 square in the other direction, it's got lots of detail in that direction. So it's high frequency in the vertical direction and low frequency in the horizontal direction. If I go over here, it's got horizontal and vertical components, which are both high frequency. If I go over here, and it's a bit hard to spot this because it's on the sky, that skyscraper is made of vertical lines, and therefore that's got very high horizontal frequency, but very low vertical frequency. So just take those for just as examples of different parts of the picture. And the way that it works in these coding schemes is to use something called a discrete cosine transform, which sounds awfully posh, but I can just try and describe it by analogy. Basically, the encoder and the decoder knows all of these. There's 64 shapes, essentially, each having 8 by 8 pixels. And if you look at them, these are the low frequency ones. This one here. The encoder knows it, the decoder knows it. You don't need to transmit them from one end to the other. Here is something that very much looks like that block of flats, vertical lines. Here is something that looks very much like the boardwalk, horizontal lines. And the point for these basis functions is that you can mix them. You can add 20% of one, take it away from 10% of another, add 30% of another, take 40% of another. And you can create any shape of 8 by 8 blocks in order to represent an exact replica of the original image. So what you do is you send these really accurately, the low frequency ones. You say, I want 23.2% of one of those, please. But out here, these are the high frequency ones. You don't particularly care because you can't see if they're in error. You can send them very clearly. Just send 10% of it. I don't particularly care. And so by doing that, you can very quickly take advantage of the deficiencies in the human visual system, where you accurately represent the low-frequency components, but you very crudely represent the high-frequency components. And that gives you a massive data saving, because you only have to send one instruction to say how much of each basis function each used. So that's a very quick description of how DCT works. And I apologize, this is the only detailed block diagram in the presentation, but the reason for showing you it is this architecture is the architecture that has lasted the past 30 years. Every single coding algorithm that has been standardized in the world since we started working in 1984 is based exactly on this architecture. Here's the video input. You subtract the previous frame from it, so you get the frame differences. You do that funny DCT thing where you send different amounts of each of the basis functions to the far end. Here, you try and work out where the image has gone, so by comparing the previous frame, moving it about a bit, and sending to the transmission link displacement vectors. And that architecture was originally proposed by Anil Jain from Michigan State University in 1981. And then also a gentleman called Robert Forsheimer from Linköping University in Sweden proposed the same thing at exactly the same picture coding symposium conference. Robert Forsheimer had a student and realizing the importance of it. He got that student to work for about 3 years, computer simulating this architecture of discrete cosine with motion compensation, and brought it back in the picture coding symposiums of 1983 and 84, and that's the basic. But what's really interesting is that basic work in the 80s has never been really beaten in the standards work since. There's lots of enhancements, but the basic architecture of H.261, H.264, H.265, all of the generations of that is actually based on this architecture. So now I'm going to talk very briefly about some of the coding schemes that didn't quite make it, because I think they're interesting and they probably will come back in some form in the future. The first one I'm going to talk about is fractal coding. A fractal is something which happens in nature a lot and really means self-similarity. So if you take a tree, it's made of trees. And I'll try and describe that. You can take a tree, it's still a tree. You take a tree, it's still a tree. And that brings on the thought for the image coders, well, why don't you describe an image as made up of pieces of the same image? Pieces of the same image which are changed in some way, morphed in some way. But is that possible? And the fractal coders went off to try and do this. And I have to say that they turned out to be relatively successful. This is a mathematical function describing a fern. A lot of people, when they're referring to fractals, use ferns. You could also use snowflakes and other things to do the same. But I'll just play the mathematical function to prove the point. It doesn't matter how close you get to this fern, it is a fern. After a while, you need a medical attention. It just goes on and on and on, and you think you're getting close, but it turns out to be another fern that follows it. And the point is, it is true that a fern, if you look at a fern and you look at it under a magnifying glass, you'll see it's made of ferns, and you can look at the ferns and there's ferns. I'll stop it because otherwise we definitely will need the ambulance. So here we go with my description of a fractal codec using the bridge scene again. So I'm going to propose in my fractal coding system four things that I can do to the blocks. So I can take a block of image, so I'm taking that top row, and I can shrink it vertically, or I can shrink it horizontally, or I could actually probably shrink it diagonally and a few other things. But a squashy type function I'm going to apply to that part of the image. I'm going to take another part of the image and I could change the brightness or change the color or change the contrast of it. And that's the second thing that I could do. Third thing I could do is change the symmetry of it some way, rotate it around its center axis, or rotate it against its horizontal axis, or rotate it against its diagonal axis. I could do lots of different things. And the final thing is just straightforward linear rotation. And even with those 4 functions that are available to an encoder, it turns out that you can actually describe the whole image by instructions using those different distortions which come from the image itself. So you take a piece of one part of the image and you say rotate it and shove it over there, change its colour a bit. Take that bit, just shrink it a bit and move it up. Take another bit and rotate it. Take a bit of the block of flats and turn it into a bit of the flag. And what's interesting is you don't ever have to transmit the picture to the decoder. The simple instructions that is iterative over millions and millions of times over and over again in a recursive nature for all the image will always create this image. It doesn't matter whether you start off with a different image, it will form this image. If you started off with noise, it will form this image. So you don't ever have to transmit the image, you just have to say what the instructions were for self-similarity within the same image. And it blows your mind, but effectively it does actually work. And there were people turning up with computer simulations of this in the standards cycle that we were working on from 84 through to 89 on H.261, and showing that this was actually quite good. The problem with it is it's tremendously computationally intensive, and we didn't have much computational intensity in those days. But there is a chance that some aspects of that will come back, because it's particularly good at describing pictures that are hard to code in nature, trees and so on. So that's fractal coding. Second way to go is lossless. We tend to think of images as trying to create them so you can't see that they've changed. They look like the original. A different way to go is to have lossy coding. It's a slight abstraction on the way that lossy coding should actually be used, but nonetheless it work here. There are circumstances where you can modify the image to make it much easier to code. And the circumstances that Don Pearson, Professor Don Pearson from Essex University was working on at the time, was the hearing impaired people couldn't use telephones. And was there a way that we could think about putting images over a telephone line with very, very low bit rate interconnecting the two telephones? You could get one of those acoustic coupled modem things that you put your handset on and then you squirted a sort of a trilly noise down it, and you could get a couple of kilobits per second from one end to the other, which would mean that people that were hearing challenged could perhaps see each other and communicate. But the way he did it was to essentially modify the image radically. So the picture that you see at the bottom left is what one end sees. The picture you see at the bottom right is what the other end sees. It's just simply edge detected video, but it becomes much easier to code, and people could sign from one end to the other and perfectly adequately use this level of resolution and detail in order to essentially talk to each other using a very low bitrate video. So that's a completely different direction in order to go. Now, the good thing was people like Harry Robinson at BT Labs had spent years earlier in the late 60s working on facsimile coding algorithms, and this black and white image with long straight edges is absolutely perfect instance for facsimile type codings to be applied to. So that's how it worked. So that's another way to go. And then the final way to go, which I'll just very briefly touch on, is an image compression method called model-based coding. Now, we started off by saying you can't compress data by just looking at the data by more than about 10 or 20%. Well, that's true. If you want to do 1,000-fold compression, you've got to look inside the data and recreate the image, and then do what we've been talking about, send the moving areas, take advantage of the human visual system. The next step is to look at the objects within the image, so understand what the image is made up of in terms of its objects, and move the objects around. And back in the mid-80s, again, this gentleman, Robert Forsheimer, brought to the Picture Coding Symposium the work on model-based coding, and this is a couple of bits of his work. Firstly, what you do is you look at the image using some analysis technique to work out where things that are important to you are in the image. So you can see This is mapping eyes, lips, mouths, noses, and so on. But once you've got that vector set, if you understood what the image was made up of in a 3D sense, you could just transmit the vectors, just the little, effectively the equivalent of the muscles, in order to move the object at the far end about, rather than send the image itself. And that was an early version of model-based coding. This is also from 1984. A gentleman called Oliver Philander who spent time building hardware in order to be able to detect his own face, so he would train it in this way. He would look for the moving areas, and we recognised those from the motion compensation work in order to work out where everything would move. And then they tried to map it onto a 3D model of the result and control it. Unfortunately, computer power in those days was significantly less than it is today, but nonetheless, the idea was that you could take the original head, work out where it was going, and then move another head at the end using hardly any bits per second. And it worked. It was very impressive for the time, and I'll talk at the end just about how this now might be used. I just want to reflect on this business of why you now get such much better performance when you watch Netflix or YouTube on a non-real-time video system. When you encode a video, if you're doing it in real time, you're constrained to the bandwidth that's available to you immediately. If you watch Netflix or any other downloaded movie, it has a fantastic advantage that there are quiet bits in it. Here, the bottom end here of this sequence, look, there's a quiet bits here, not much going on. It's probably a dark scene with hardly any movement. And then there's really highly active scenes which are taking, maybe 10 times the bandwidth, maybe 400 kilobits up to 4 megabits per second there. And these movies have the advantage that they're non-real time, and therefore you can just take the average bit rate and have really a lot higher bit rate at the peak times within the movie where you really need the quality. And rather than reduce the quality, as you saw in the Tomorrow's World video, where the guy was waving his arms about and you lost video quality, you don't have to do that in a film sense of non-real-time video. And that's a great advantage to the broadcasters. So if you're watching your video download and it's doing this, it's probably not your internet that's stopping and starting. It's the fact that there's far more bits being loaded for the more difficult parts of the sequence, and the access in this case is time. So I just thought I'd just mention that at this point. So I talked about the video codecs that have been developed. H.261 is off this scale. It's pre-1996. Very quickly after H.261 came MPEG-2, which is used in your DVD players and on your CDs and so on. And what happens is the video codec comes out and hits a certain bit rate, and then people learn how to optimize that very standard codec and get quite a lot more out of it. So we started off for an HD video requiring something like 40 megabits per second. But after 8-10 years, then people could get the same quality video down only 15 megabits per second. But then you run out of runway. There isn't any more optimization to be done, and a new standard comes out based on exactly the same architecture as it happens. H.264 came out, and then high efficiency video codec H.265 came out in recent years and will improve. But the learning profile is the curve that goes from the top to bottom, and I'm thanks to Mike Nielsen at BT for providing me with this curve. And it begs the question is, are we reaching the point that we just don't need any more video compression? I mean, we need what we've got, but bit rates are getting higher. This is an HD TV. I don't know about you, but when I'm at home with my big television on the wall, I have to get up to check whether it's in UHD mode or not, because the resolution's getting pretty good. And actually, colour depth and contrast is becoming more important these days than resolution. Well, my view is absolutely not, because the display technology is going to change, and this is the last segment of my talk that I just want to talk. Holograms. Now, this is sort of science fiction. Mimesys here put it on their website to describe how you can't do it and it won't happen. And certainly 3D projections of holograms in this way is very unlikely in the next 20, 30 years. There's nothing on the horizon that's looking like it's going to be delivered it. And companies like Mimesys are working on virtual reality solutions for workplaces, productivity tools, those sorts of things, using VR headsets, which are incredibly inconvenient. And we've all tried to use the 3D glasses in order to watch your television, which sort of work, but they're pretty inconvenient as well, and haven't caught on as well as people would like. But what is happening is something called light field technology. There's cameras out there now that you can take the picture and then decide what you want to focus on after you've taken the picture, because what it does is it takes literally hundreds of pictures through the focal plane of the same image. So you can take them home and then choose your focus and your depth of field setup in retrospect. It's analogous to the reverse of that. There are companies like Looking Glass, a new tech company in California, that by Christmas will be bringing out a 10-inch by 8-inch glass display, which has multiple layers in it across the focal plane, and in this case projects 45 different images in parallel in order to give you a 3D effect. It's designed for gaming, but also is intended for use for looking at the thing that you're going to print on your 3D printer that will take a day to print before you actually print it. So it's 10 by 8 inches. This is a picture of a real one. It's got 45 concurrent images reconstructing this image, so you actually end up with a 3D effect. They intend it for gaming initially and sort of playing around with, but it sort of demonstrates the concept. But here the point is that you've got 45 times the bandwidth requirement of a single image, because parallel images are actually within the display. And another company, Lightfield Labs, are working on a 20-inch by 24-inch display by a couple of inches thick with a pixel resolution of 650 megapixels. Now, your average iPhone has got 12 megapixels, something like that for your iPhone. This has got 650 megapixels. And if you do the maths on it, 8 bits per pixel, 25 frames per second, 650 megapixels, you end up with 0.3 of a terabit required in order to be able to feed a display like that. So you can very quickly see that we're going to be into multiple terabits per second requirement for displays that are home-sized, 24-inch, 30-inch displays to put on your screen. And if that happens, then good luck with rural broadband. It's going to be some challenge. So we are going to require the video compressors in order to solve that challenge. Otherwise, you're just going to end up with local displays. And the likely solution to it is going to be this model-based coding, getting inside the image, understanding how it behaves, and then controlling the behavior rather than looking at it as an image in its own right. So I just want to finish with my very, very last slide. You'll be pleased to know. The slide comes from a presentation that was done at the last Eng talk here in this theatre, also a very packed theatre actually. A gentleman called Hal Lee from the Vision Lab at the University of Southern California came and gave a talk about the digital human. And the work that they were doing was really for the film industry, looking at CGI graphics. Inserting people into a film that didn't ever appear in the film is a key challenge. There's been a number of films out recently where that has been done, and making that look realistic. So for different reasons, they've been working on this model-based problem, looking at the model. The picture on the left is the original. That's a 2D picture taken from an iPhone. And I'll show you it moving in a minute. The picture on the right, there's only ever been one image sent to the decoder. So this is a recreated image on the right-hand side, where only one image, the original image that you see there, was sent to the decoder. Everything else that happens in the right-hand image is a result of something called deep learning, where you use machine learning to understand how the object moves in the encoder, sends control information to the decoder, and there's a 3D model of a human in the decoder, which isn't this person, right? And it's all done on computer in fairly rapid time. So just watch this. Watch this. Watch this. There should be sound on it.
Sort of pin screen, getting my face scanned, or rather actually just photographed on an iPhone, which is great, don't get me wrong. I'm just used to bigger cameras with more tech, not just one being held in someone's hand with a Mickey Mouse back on it.
So you really are getting to the stage that you don't have to have the image at all. You can just have a sort of a computer model of an image and then control it in this way. Even if you don't think that the right-hand image was good enough in order to watch in real time, if you go back to my original prediction algorithm, you could make that the encoder and the decoder predictor and then only send the differences between it and the real image in order to correct the differences. So there are ways that we're going to end up with literally 10,000s, hundreds of thousands to one compression if we need it from this image coding profession. So thank you very much for listening. I look forward to questions.
So, ladies and gentlemen, some of you may remember me. I'm a past president, 2016-17. I'd like to thank Mike very much indeed for a hugely informative talk, and certainly somebody who'd been involved in signal processing, not this particular field. I found it really very engaging indeed, so thanks for that. So for this Q&A session, we've got about a quarter of an hour or so, and I'm reminded here that we have a hashtag, which is hashtag IETEngTalks. That's one word, lowercase. And so anyone who wants to use that, we have somebody watching out for Twitter feeds and so on, and your questions we've fed into this session. I've also got this rather strange device, which is a first for me, which is called a catch box. And what we're going to do, it's a microphone. You need to talk into the top of it to be heard. I'm going to lob it across to Freddie, who's going to identify himself. And he is going to lob it to you. So with that, I'm going to open the questions. Would anyone like to? One over there, so it's Will Stewart.
Ah. No, you're not.
Mike, thank you very much. Lovely, lovely talk.
Okay.
You talked about a third of a terabit as the third of a terabit?
Yes.
We've been able to do petabits on the same fibers. Those are the ones that GigaClear is installing to our local villages.
Yeah.
So you can do these numbers.
Yeah.
Actually, I doubt you would ever try and do that, but it does beg the question of whether you really need so much compression if we could do 100 gigabit, which is routinely available now.
I quite agree. There's an intersection, really interesting intersection happening between data rate increasing and the cost of data falling and the ability to do image compression. It won't be impossible, but 2 terabits per second is 1,000,000 times more than 2 megabits per second. So there's got to be some fundamental cost change with routing and all the other things in order to make it really economic when you're multiplying something by 1,000,000 times. So I agree, but it's always has been. When I first joined the research labs, the biggest, most difficult question to answer was, we're working on fibre optics, why are you bothering with this stuff? Right? And here we are, 35 years later or something, with everybody still using video compression and it being in every piece of electronics that you ever used, including my doorbell, by the way. Yeah.
Next one. Just here.
Yeah. Whoa.
Good stuff.
Mike, very, very interesting, and takes me right back to the days when we were working on that stuff. I just want to touch on something that was in the Tomorrow's World video, and something that I don't think any of us who were working on that stuff in those days would have predicted, was not only can you now do it, but you do it for free on FaceTime, Skype, whatever. You don't pay any money to BT or anybody else to have video conferencing.
Yeah, indeed. Yeah, the business... the business models in all respects are not what you would have expected. as I say, I mean, the biggest dominant use of all the technology is actually broadcast, and actually at the time the broadcaster says don't need it, and you're ending up with all sorts of models that are happening. But I mean, you could say we're getting 1,000 to 1 compression, and the reason that they can offer it free is because it's 1,000 to 1 easier for them to store. I just can't imagine. And a statistic I came across when I was doing the research for this talk is for every second that passes, there's 5 hours of new video goes on YouTube, right? So every second there's 5 hours. Just imagine the storage farms and the energy that's being required in order to be able to store those petabytes of data, in the middle of this desert somewhere. And all I can say is it would have to be 1,000 times bigger. I sort of helped a bit.
Thanks, Mike. Do we have anyone online yet coming in? Twitter feeds? Not yet. Okay. Anyone else? One gentleman in the middle there. I think then the next one is in front. Oh.
Well, just add my comment. Superb talk. You talked about video coding, video compression, of course. Most communication isn't purely video.
Right.
The communication, without getting into smelly telly, most communications are both image and audio. Yeah. And there is an interplay between those that you didn't talk about exploiting, the perceptual coding aspects and so on. Do you want to say something about that?
I'll try. I mean, it's for certain. It's certainly if you treat the problem as a whole in a model sense, then what you're pronouncing and what's happening to the image and what the sound sounds like are all coupled. So there is an opportunity in order to get in there and do something which is at the cross section. Fortunately, image compression these days had a bigger and bigger challenge. Actually, audio compression hasn't had anywhere near the same amount of challenge, simply because we've always had the same spectrum of audio that we've always wanted to transmit, where video is increasing. But I think that's just as well, because I don't know whether you noticed, but I can detect even slight deficiencies in the audio, and I don't necessarily detect the deficiencies in the video when I watch my BBC News television channel at home. So you're probably, the opportunities there for further compressing audio are far more challenging, and the bit rate that you're starting with is less. But I agree, for model-based coding, you could absolutely think about combining the two. It's one whole live object, and think about the resonance of the vocal cords and how stretched they were, and send that instead of the sound. All of those sorts of things are quite possible. Yeah.
Thank you. I think yes, there's one there, and I think there's one there. Gentleman in blue shirt first, if you just in front of Sir John. Yeah? Just here. Would you like to wave again?
Yeah,
That's
sorry.
it.
I'd like to add to that comment over there, and possibly Will's comment. I think I've used the video conferencing system which you developed and at Marconi, and one of the things that we discovered is that we would set the thing up to 128 kilobits per second ISDN.
Yep.
But if you had it on 64 kilobits per second as a total bandwidth of audio and video, what you discovered, to my surprise, and maybe you can confirm this, is that the video was only 4 kilobits per second, and the audio was 64. Sorry, 660. So basically, they took the view that if you had a video conference with somebody in Japan, it was more important that the audio was correct, even if the picture was moving around and it wasn't brilliant.
I totally agree. I mean, as I say, because the effect that Will Stewart said, that bandwidths have gone up, and there hasn't really been as much attention on the audio compression as in the other areas, albeit more difficult. But I agree. I absolutely know the effect. At 64 kilobits, you needed probably, as we were building those codecs, 32 kilobits for the audio, and then you need some control information, and you were left with 18 kilobits or something for the video, which is pretty impossible from where we were sitting at the time. It can be done now, though. I mean, there are pretty good quality Skype calls going on at 64 kilobits, including audio, and it's just because the technology moved a lot more.
Can I just say one other thing? In terms of what Will said, if you look at the issue where bandwidth is key, at the moment in home usage we have VDSL, fibre to the home. There are technologies which enable you to have higher bit rates to the home. What's a more difficult area is using a mobile phone where you've only got 4G coverage. So the mobile usage, when you're not using Wi-Fi, is a more challenging situation, isn't it? Trying to get that when it's real time, which is what you said.
But the fortunate thing is, and it's really good, isn't it, that mobile devices tend to be small, and therefore the resolution can be a lot less. So you actually think of the video that you get from your phone. It looks good, but it's tiny. You're not sitting and watching it on a 65-inch HD display, as it were. But delay is always the problem, and that's always been the problem with our video coding schemes. I tried to bring that out, is that any delay across the system when you're trying to have real-time communication makes you look pretty stupid, and you don't get the interaction that you would otherwise get.
Thank you. I think, yes, the gentleman here in the middle. Thank you.
Audit. Is this the right end? Yeah. Talking about the opportunities for further work, it struck me that that there's a great benefit in the current system in that the receiving end, the reconstructing end, is relatively lightweight, whereas the transmitting end has to do all the grunt. Now that's great for broadcast, great for DVD manufacture, etc. It doesn't work so well when your transmitting system needs to be small power, not power hungry. Things like little drones, big drones for that matter, lots of cameras all over the place. So at the moment we've got asymmetry in one direction. The challenge, I think, is to create a system that's asymmetric in the other direction.
I agree, and that's. I could have talked more about the fractal coding algorithm, and the problem with the fractal coding algorithm is actually there's almost as much technology required in the decoder as there in the encoder. So they hit the symmetry target. It was just that we're both complicated, right? Which didn't. But actually, technology's coming to our rescue. I bought a doorbell for, I think it was £110. It's called Ring. It's got video in it. It's a full H.261 encoder in it. It runs on a battery. It's in the doorbell behind the button, and it lasts for a year on the single charge of the battery. And so I think, as always with science questions, you sometimes end up focusing on a problem that somebody else is going to solve, and that's certainly what's happened with chips and memory. I think the big driver for video coding is going to be this 3D effect displays. I can't imagine another one at the moment, because if I came along with a business case and said I can now do HD video over 1 megabit per second, I don't think anybody would bite my hand off, because they've got 2 megabits per second, and it's we're sort of plateauing out in terms of the mid bandwidth. Maybe from a storage point of view it might be useful, but from a transmission point of view I doubt that's the case. And come back to Will Stewart's point, I've got 55 megabits going into my house in a rural area now, only in the past few weeks, but I have now got it. And that's probably more than I'll need for a little while at least. Other questions?
Thank you. There's one just here.
In your last demo piece,
yeah.
We're kind of seeing things like AI learning engines in the cloud.
Yeah.
Are we going to get to the situation where we don't know how it's actually compressing and sending images?
Yeah. I mean, that's a very interesting area in its own right, because we have got to the stage that the bandwidth is big enough to transmit the algorithm before you transmit the video, and the general computing capability of your laptop or your smartphone or whatever, they don't really put special technology in there anymore in order to do video stuff. They just do it on the processor. So you are at the stage that you don't necessarily have to pre-agree a coding standard, because you can send the computer program that represents the compression algorithm just an instant before you actually send the compression algorithm. So that's absolutely true. The way that I thought you were going to go, which was actually the subject of this previous Eng talk, which you can watch on IETV, is about the fact that you don't even know that you're talking to the right person. Because if you apply those vectors that came from the right-hand image to a picture of somebody else, then they'll say all those same things, right? So there really is. Fake news is an interesting problem in print. But if you really get realistic people saying things that you don't expect them to say, and they didn't say, then you've got a whole new range of interesting challenge. And as I say, Dr. Howley, that's exactly what he focused on.
Thank you, Mike. I think we have to wrap up there, looking at the time and drinks waiting for people outside and so on. So I would first of all like to direct my thanks to you, and rather than giving an hour-long lecture thanking you in terms of technical detail, I think certainly I've been hugely informed. I think as video consumers, we're all video consumers, are hugely grateful for the work you did so formatively those years ago, and continue to advance in your current thinking and dialogues with researchers. So I think that's an immense achievement, and we're very grateful to you for that. So I think I'd like to say best thanks to Mike on behalf of this audience and the institution for a really great talk. And it's been a great way to begin your presidency, I think. And we wish you all great success as you go forward into your year of office.
Thank you very much.
And so finally, I should say some words of thanks for the outgoing president, Nick Windsor, who's done an absolutely fantastic job over his year and has really added value, has felt the honour of the position. We were talking to him before this meeting, and I know that he's led the trustee board superbly well. I've had the pleasure of being on that and the honour of being on that board for the last year. I'm going to say a few more words upstairs, but I just wanted to make sure that we all acknowledged, on behalf of the IET, our great debt of thanks to Nick. Thank you. So finally, I think has the slide been up already? So announcing, okay. So this is the next Eng talk that's coming up. I believe it's very heavily subscribed already. So if you've got an interest in attending that talk, which promises to be extremely interesting, get in there early, because I think we've only got a few places potentially left for that. So that brings us to really the end of the formal proceedings. Please join us for drinks in the registration rooms. And for those of us who are staying to dinner, we're going to be called to dinner fairly shortly. So, ladies and gentlemen, thank you very much for your time tonight, and a safe journey home. Thank you.